Hello, my name is Oscar Alcantar, and today we'll be solving questions 169 all the way up to 171, or 172, I apologize. Okay. So, to start off, the position vector of the moving particle is r of t to e minus 5t sine of t, comma, e negative 5t cosine of t, comma, or e negative 5t. Okay, so the first problem, which is the velocity of the particle, is problem 169. So here, let's do this. To find the velocity vector v of t, take the derivative of each component with respect to t. We must apply the product rule to the x and y components and the chain rule to the z component. Let's do that now. X component d over t e to the negative 5t sine of t is equal to negative 5e minus of t sine of t plus e to the power of negative 5t cosine t, which is equal to e to the power of negative 5t cosine of t minus 5 sine of t. And then for the y component, we have d over dt. We have e to the power of negative 5t and cosine t is equal to negative 5e to the power of negative 5t cosine t minus e to the power of negative 5t sine t, which is equal to negative e to the negative power of 5t. I'm lost. 5 cosine t plus sine of t, correct. And for the z component, which we're going to add the chain rule to, z component we have d over t. Then we have 4e to the negative 5t power, which is equal to 4 times negative 5 times e to the negative 5t, which is equal to negative 20e minus negative 5t power. And that leaves us with v of t to e minus 5t cosine of t minus 5 sine of t, and we get minus e negative 5t 5 cosine of t plus sine of t parentheses comma negative 20e minus 5t power. Okay, to find the velocity vector, we take the component by component derivative of our position vector with respect to time. For the x and y components, we apply the product rule alongside the chain rule. Differentiating the x component gives us negative 5e to the negative 5t sine of t plus e to the negative 5t cosine of t. Factoring out the exponential term gives us e to the negative 5t times the quantity cosine of t minus 5 minus t minus 5 sine of t. Following the same process for the y component yields negative 5e to the negative 5t cosine of t minus e to the negative 5t sine of t, which factors down nicely. Finally, taking a simple chain rule derivative of the z component gives us negative 20e to the negative 5t. Putting it all together, here's our full velocity vector. Okay, now for question 170. Okay, speed is the magnitude of the velocity vector, and that right here looks like this. So we have magnitude of vt, which is equal to the square root of x prime to the power of 2 plus y prime to the power of 2 plus z prime to the power of 2. Let's square each component, factoring out e to the negative 5t parentheses to the power of 2, which equals e to the negative 10t. It looks like this. Now we're gonna do x prime power of 2, which is equal to e minus e to the power of negative 10t cosine of t minus 5 sine of t to the power of 2, which is equal to e to the negative 10t power, which parentheses right here, cosine squared of t minus 10 sine of t cosine of t plus 25 sine squared of t. And then we're gonna do the y. So it's y prime is equal to e minus e to the negative 10t power 5 cosine of t plus sine of t to the second power, which is equal to e minus to the negative 10t 25 cosine squared of t plus 10 sine of t cosine of t plus sine squared of t. Then we're going to do the z prime squared, which is equal to negative 20 e to the negative 5t power, parentheses, to squared, which equals 400 e to the negative 10t power. Okay, now we're going to sum them up inside the square root and factor out e to the negative 10t power. That looks like this. So we have the magnitude of v of t, which is equal to e to the negative 10t power, bracket, parentheses, cosine squared of t plus 25 sine squared of t minus 10 sine of t times cosine of t, parentheses, plus parentheses 25 cosine squared of t plus sine squared of t plus 10 sine of t times cosine of t, and then plus 400, close was our bracket right there. Make sure you extend the square root. Notice that the cross multiplied terms, -10 sine t and cosine t and plus 10 sine t cosine t cancel out, which leaves the magnitude of t, which is equal to the root of e to the -10t power bracket 26 cosine squared of t plus 26 sine squared of t plus 400. This is what it's looking like so far. As you can see, close your bracket as well. Now we're going to use the Pythagorean identity. 26 cosine squared of t plus 26 sine squared of t, which is equal to 26 times 1, which is equal to 26. It looks like this right here. We're going to have the magnitude of v of t, which is equal to the root of e to the -10t power, plus 26 plus 400, which is equal to the root of 426 e to the -10t root, to the -10t, and we have left over the magnitude of v of t, which equals the root of 426, and then we have e to the -5t power, which comes out to the right side. Okay. Speed is defined scalar-wise as the magnitude of our velocity vector, calculated by taking the square root of the sum of the square components to make this clean. Notice that every single squared term will contain a shared factor of e to the -10t. Let's pull that out entirely. When we expand the inner binomials for the x and y pieces, the middle cross product terms, -10 sine cosine and plus 10 sine cosine, perfectly cancel each other out. This leaves us with 26 cosine squared t plus 26 sine squared t, which simplifies beautifully to just 26 using the fundamental Pythagorean identity. Adding the 400 from our squared z component brings our total inside the radical to 426. Pulling the exponential out of the root leaves us with the final simplified speed of the square root of 426 times e to the -5t. Perfect. Now to do the acceleration of the particle, which is question 171. To find acceleration a of t, we find the derivative of the velocity vector. We will use the product rule again. Okay. So we have v of t. Wait. Yeah. We have v of t. And we have e to the -5t cosine of t minus 5 sine of t, comma, e to the -5t minus 5 cosine of t minus sine of t, comma, -20 e to the -5t power. Okay, so first we want to do the x component, which is d over d of t bracket e to the negative 5t cosine of t minus 5 sine of t bracket, which is equal to negative 5e to the negative 5t power cosine of t minus 5 sine of t plus e to the negative 5t power times negative sine of t minus 5 cosine of t. This all equals to e to the negative 5t power times 5 cosine of t plus 25 sine of t minus sine of t minus 5 cosine of t, which is equal to e to the negative 5t power times 24 sine of t minus 10 cosine of t. Time for the y component. Let's see if we have enough room here. So we have d over d of t e to the minus 5t minus 5 cosine of t minus sine of t bracket, which is equal to negative 5e to the negative 5t power minus 5 cosine of t minus sine of t plus e to the negative 5t power times 5 sine of t minus cosine of t. Okay, and then that equals e to the negative 5t power times 25 cosine of t plus 5 sine of t plus 5 sine of t minus cosine of t, which equals to e to the negative 5t power of 24 cosine of t plus 10 sine of t. Okay, for the z component, we're gonna get another paper. Okay, so for the z component, let's write that down. We have d over dt bracket minus 20e to the negative 5t power, which is equal to 100e minus 5t. Okay, so that leaves us with a of t is equal to e to the negative 5t power times 24 sine of t minus 10 cosine of t to comma e to the negative 5t power times 24 cosine of t plus 10 sine of t, comma 100 e to the negative 5t. Okay. To compute acceleration, we take the derivative of our velocity vector, applying the product rule to the x component, gives us a derivative of the exponential part plus the exponential times the derivative of the trigonometric quantities. Grouping like terms together yields an x acceleration component of e to the negative 5t times 24 sine of t minus 10 cosine of t. We execute the same product rule expansion on our y component, which simplifies down cleanly to e to the negative 5t times 24 cosine of t plus 10 sine of t. Lastly, differentiating the simple exponential in our z component brings down another factor of negative 5, resulting in positive 100 e to the negative 5t. This completes our final three-dimensional acceleration vector. Lastly, for question 172, let me mark that down. Oh, the sun's coming up. Anyways, so an automobile is traveling forward at a constant linear speed of v car, which is equal to 55 miles per hour. Let's write that down. 55 mph. A point on the circumference of the tire undergoes two simultaneous motions. 1. The linear translation forward at 55 miles per hour, and 2. Rotational motion relative to the center at a tangential speed equal to the car's forward speed, assuming there's no slipping, which is also 55 miles per hour. At the absolute top of the tire's rotation, the forward translational velocity vector and the forward tangential rotational velocity vector align perfectly in the same direction. That looks like this. Vmax is equal to V translation plus V rotation. And then Vmax essentially equals 55 plus 55 mph, which is miles per hour, giving us a total of 110 miles per hour. For this final problem, we need to analyze the kinematics of a rolling tire without slipping. The center of the tire moves forward at a constant linear transitional speed of 55 miles per hour. Simultaneously, relative to that center point, every point on the outer tread is rotating tangentially at that exact same speed of 55 miles per hour. The maximum speed occurs at the absolute peak of the tire's rotation. At this top dead center position, the forward transitional velocity vector and the forward rotational tangential velocity vector are perfectly parallel, pointing in the identical direction. Therefore, we simply add the two linear speeds together, 55 plus 55. This means the peak instantaneous speed of a point on the outer edge of the tire is exactly 110 miles per hour. And that is all. Thank you. So here's